In this video, we're going to look at the mathematics of sound, particularly the mathematics of standing waves as they apply to strings and tubes. A lot of this has a practical application in musical instruments, but we're going to just go ahead and break it down into strings and tubes. Now, starting off with strings, you probably remember from your lab that when you take a string and shake it back and forth at just the right frequency, you can create these patterns called standing waves. The first one is what you get when you get a wave that kind of looks like this. It's bouncing back and forth. We said in the conceptual video that the places that don't move are called nodes, and the place that you have the biggest amplitude is called an antinode. Now, if I increase the frequency on this same string, I will get a pattern that looks more like this. And here you see that I have 3 nodes and 2 antinodes. If I keep increasing the frequency, I can get up to something that looks like this that has 1, 2, 3, 4 nodes and 3 antinodes. Most people find it easier to describe these in terms of the amount of antinodes because there's 1 of them, 2 of them, and 3 of them. And I agree that's probably an easier way to describe these different patterns that we see. Now, one of the ways of talking about these different patterns is we call them modes of vibration, or sometimes when it's in a musical sense, we'll actually call them harmonics or overtones. They mean similar things. When I see a wave in this first pattern, I'm going to call this pattern 1, pattern 2, and pattern 3, I only see 2 nodes and 1 antinode. If I was to draw a complete wavelength of a wave, it would start and come back to the same place, and that would be 1 wavelength of a wave. If I complete the pattern, you're going to see that that includes 2 nodes and an antinode. This here is 1 wavelength, which means that the distance between any node and antinode is a quarter of a wavelength. So when I look at this pattern up here, number 1, I see 2 of those intervals, which means I have 2/4 of a wavelength or half a wavelength. For my first pattern, the length of that string corresponds to a half a wavelength. And so the wavelength of this string is 2 times its length. In the second case, I have 4 of those intervals, which means I have 4/4 of a wave, which means I have 1 entire wavelength. And so the length of the string is the wavelength. If I rewrite that or flip it around, the wavelength is equal to the length of the string. For number 3, I have 6 of those intervals, so I have 6/4 or 3/2 of a wave on here, which means the length of my string is 3/2 the wavelength, which makes the wavelength 2/3 the length of the string. And I can keep going, but I'm actually creating a pattern here. And the pattern is that the wavelength for any given mode, and write a little n to represent a generic mode number, is equal to 2 times the length over that number. So for instance, for 1, we had 2 over 1, or 2 times the wavelength. For 2, we had 2 over 2, which is 1 wavelength. And for 3, we had 2 over 3, which is 2/3 the wavelength, and so forth and so on. If I got up to number 5, the wavelength would be 2/5 the length of the string. What we're going to do with that pattern is we're going to go back to our equation for the velocity, which is, on a string, the force of tension over the mass per length. The wave equation says that the speed of the wave is equal to the wavelength times the frequency. So for instance, if I have frequency 1, I can substitute in that the wavelength is 2L, and if I make that substitution up here, I get that 2 times the length times frequency 1 equals the force of tension over the mass per length. Solving for F1, I get this. Now, F1 has a special name. We call this the fundamental frequency. If you were to take a piano string and pluck it, the frequency that you would hear the most would be the fundamental frequency, which you can calculate this way. To get to the second frequency, We just have to substitute in the different wavelength. I don't feel like I need to go through this entire derivation for you because it's in your book, but the pattern that emerges is that F2 will be twice the frequency of F1. That's how we get this pattern right here. And then F3 will be 3 times the frequency, which is how we get this pattern here. And finally, the generic Fn equals n times F1. This would be called something like the second harmonic. This would be called the third harmonic. I don't like using the overtone notion because it's confusing. What we call the second harmonic, some people call the first overtone. That's the last thing we need, is to start mixing up our numbers. I just don't think it's a good idea for beginning students to have to deal with that. It's not like it's beyond you, but it's just it causes a lot of confusion. Now, this pattern holds for all strings. So once you find this first frequency using this formula, you can find all the frequencies that come after that very simply by multiplying them by 2, 3, and so forth and so on. An example would be if F1 was 200 hertz, then F2 would be 400 hertz, F3 would be 600 hertz, and say F10 would be 10 times 200 hertz or 2000 hertz. So you get the idea. It's actually pretty easy once you get the first fundamental frequency.